All right, so we are going to be doing some Maclaurin polynomials. We're just starting these off today. A Maclaurin polynomial is something, it's a polynomial, and all of its derivatives are based at the value x equals 0. That's what makes something a Maclaurin. So if you look at our format here, all of the derivatives are taken when x equals 0. So our first question says, write a Maclaurin polynomial of order 3. Now, order 3, the order, that's just a fancy way of saying, please take 3 derivatives. So that's what we're going to do. We're going to take the first derivative and the second derivative. And the third derivative. Okay, now, since it's Maclaurin, that means all of these derivatives are going to be evaluated when x is equal to 0. So here's our results. And all that's left for us to do is to write these into the Maclaurin polynomial. So f of 0 is 1 plus the derivative over 1 factorial times x to the first plus the next derivative value over 2 factorial x to the second plus 8 over 3 factorial x to the third. Now you'll notice a couple things that the value of the exponent matches the value of the factorial. We can simplify this a little bit. Okay. And this is a pretty good approximation for f of x, of e to the 2x. In fact, let me go ahead and look at this on the calculator. On the calculator, you can see up here, I've got e to the 2x, and I'm going to say, what's the answer when x is 0.1? Calculator tells me what it is. Now, here's our Maclaurin polynomial. When I put a 0.1 in, there's the answer, very, very close. If I wanted to get a more accurate answer, I would just add a few more terms to this. Now, again, our derivatives were taken when x equals 0. So when I plugged in numbers here, I took a number close to 0. Let's take a number that's kind of far from 0, like let's say 5. When I put a 5 in, this is the answer for the function. And in our Maclaurin polynomial, when we put a 5 in, this will get, notice, not very close at all. Again, we're going to get into this later about our radius of convergence and so on, but generally speaking, we need to build these polynomials very close to the values that we're trying to find them at. So if I wanted to find the answer at, say, let's say I wanted to find the answer at 5.3, what I would have done is built the polynomial centered at 5.0, very, very close to 5.3. All right, let's get back to this one and build a few more. Because again, today we're just about building these. So here's our second one. Write a Maclaurin polynomial of order 4 for f of x equals sine of x. All right, so that means I need to take 4 derivatives. Whoa, what happened there? So our first derivative. Third derivative. And then our fourth derivative, and we're not going to keep putting apostrophes up there. We're going to start putting numbers up there after the third. Now, since this is a Maclaurin polynomial, that means we're going to evaluate all of these when x is equal to 0. Well, the sine of 0 is 0. Cosine of 0 is 1. 0. Negative 1 is 0. There's our values. Let's go ahead and put them into our Maclaurin polynomial. And if I simplify this down, we get x minus 1/6 x cubed, and that's it. So this brings up an interesting question. We did take 4 derivatives to give us an order of 4, but this is a degree of 3. So you've got to be clear, like the order really means how many derivatives to take. So an order 4 polynomial for this would be the exact same as an order 3. Kind of a nice thing to take a look at again on this. If I go back to our calculator, no, not that one. Let's do a different one. Okay, so here's what we have, right? Here's our sign, this one that we were building, and this is an order 1. So what I've got it set up as, I've got it set to find the Taylor polynomial and also to draw it as well. And you'll notice as we add more derivatives, we're starting to get really close to this graph of sine. In fact, for sine, its radius of convergence is pretty big, right? If I keep adding more and more terms here, I'm going to get it to be approximated an answer as it gets further and further out. That's what we're doing here. And you can tell there's definitely a range in here, an interval where this is working based on those terms. Now, if I go outside of that, it's going to be pretty far apart. And again, that's a topic for a different day. Now, we can change the center of orientation, right? The center of our polynomial. This is for e to the x, kind of like we did earlier, right? I can change the center. Right now, it's a Maclaurin, right? It's centered at 0. But if I make it a Taylor polynomial, Taylor polynomials, all they are is things that are centered somewhere else. So if I make it centered at 1, I can tell as I'm adding those derivatives, it's getting pretty close in there. But after a while, it doesn't get any further. And as I change that center, where I'm basing my polynomial at, I can see what's happening here. And again, this is our first day doing this. So let's do one last build. And that's this one, right? So now we're going to do a Taylor polynomial. And I want a third degree, meaning when I'm all done, I want to see an x to the third power. Now notice this one is centered at 2. Now I've kind of done a duplicate of my entering. Third degree and order 3 mean the same thing. We're never going to really have both of those there, but they mean the same thing. Notice a polynomial. It's just like the Maclaurin, except the derivatives will be at whatever we're dealing with. In this case, c is equal to 2, right? That's what we're centered at. C is the center. And instead of being x to the first, x to the second, x to the, it should be a 3 here, x to the third, we're going to have x minus the center, right? So x minus 2's will be in there. Well, first things first, we need to find 3 derivatives. So the first derivative is -1 over 3 minus x. Remember that chain rule. And I'm going to rewrite that to help out with my other derivatives to be this. That's just going to make finding those other derivatives a lot easier. Oops. And again, we're doing an order 3. So third derivative. That was odd. Sorry about that. we're going to evaluate all of these at x equals 2, right? Because that's what our center is going to be at. Well, the natural log of 3 minus 2, 3 minus 2 is 1. Natural log of 1 is 0. This will be -1. This will be -1. This will be -1. So our polynomial is going to be 0 plus -1 over 1 factorial times x minus 2 to the first, right? Because again, we're centered at 2, so we need to change those. Plus -2 over 2 factorial, x minus 2 squared. But all kinds of issues here. And let's see, whoops, wrong term there. And then lastly, our third derivative has a value of -1 over 3 factorial x minus 2 to the third. So that simplifies all down to being the following. But I really got to figure out what's going on with this computer here. Sorry about that. There we have it. That's our third degree Taylor polynomial. Order 3, centered at 2. Okay, there's an assignment to work on. Please do well.